captions in English, please. So this is the fourth video of chapter 9. And so we will cover more on limiting reactant and theoretical yield using mass, but also percent yield calculated from actual yield and theoretical yield. So in many industrial applications, the more costly reactant or the reactant that is the most difficult to remove from the product mixture is chosen to be the limiting reactant. So we want that reactant to be completely consumed. So when working in the laboratory, we measure the amounts of reactant in grams, right? We go to a balance and we weigh our substances. We are not counting moles or molecules. So to find limiting reactants and theoretical yields from initial masses, we will add two steps to our calculations. And those two steps will involve the molar masses of the substances. So we need to know the formulas of the reactant and product. So let's go through an example. Example 6 here. So if 53.2 grams of sodium and 65.8 grams of chlorine react to form NaCl, sodium chloride, what is the limiting reactant and theoretical yield? And so you're provided the chemical equation that shows how two sodium solid react with chlorine gas to form two NaCl solid. So NaCl is sodium chloride or table salt. So when you want to find the limiting reactant and you're given masses for both reactant, you need to calculate how much product can be produced from each reactant. So let's start with sodium. So because the sodium is not given in number of moles, but in grams, and because the relationship between sodium and sodium chloride is given in moles, it says that 2 moles of sodium will make 2 moles of NaCl. So to know how much product we can make, we have to change first the grams of sodium into moles of sodium. And for this, we use the molar mass. And remember how the molar mass is never provided to you. You have to find it in the periodic table. So always have a periodic table available. So by using the molar mass of sodium, you will change the grams of sodium to moles of sodium. Then, now that you have moles, you can change the moles of sodium to moles of another substance, and here NaCl. And you use the coefficient of the chemical equation for that. And as I said, 2 moles of sodium will produce 2 moles of sodium chloride. So you use that as a conversion factor to change moles of sodium to moles of sodium chloride. And then once you have your moles of sodium chloride, you convert them back to grams of sodium chloride using the molar mass of sodium chloride, so NaCl. So this will allow you to calculate the amount of product from the given amount of sodium. You do the same thing with the chlorine. So you take the 65.8 grams of chlorine and we'll change them to moles of chlorine using the molar mass of chlorine. So chlorine, notice how it's Cl2, it's a diatomic molecule. So you take twice the molar mass of one chlorine atom, and that's 70.90 grams of chlorine per mole of chlorine. Then once you have the moles of chlorine, you can change them to moles of NaCl using the coefficient of the chemical equation. And here there is, you need only 1 mole of chlorine to make 2 moles of sodium chloride. And then you again change the moles of sodium chloride to grams of sodium chloride using the molar mass of sodium chloride. And once you have done those two calculations, you will compare the amount of product that is formed in each case, and the smallest amount will determine the limiting reactant. So let's do this. And here, let's start with sodium, the 53.2 grams of sodium. So that's your given amount. That's what you will start your calculation with. Multiply by the first conversion factor that is from the molar mass of sodium. and you place the 22.99 grams of sodium on the bottom of the conversion factor because you want to cancel units of grams of sodium, and that's per mole of sodium. Multiply by the second conversion factor that has the moles of sodium on the bottom because you want to cancel moles of sodium, and the 2 moles of sodium chloride on top. And then the third conversion factor will have the moles of sodium chloride on the bottom because we want to cancel the units of moles of sodium chloride. And then the grams of sodium chloride on top. So the molar mass of sodium chloride. So in the calculator, you do 53.2 times 2 moles of NaCl times 58.44 grams of NaCl divided by 22.99 Na and divided again by 2 moles of Na. The calculator answer is 135.233. We need to keep 3 sig figs because there is 3 sig figs in the given amount, and both molar masses have 4 sig figs. And then the 1, 2, and 2 and 1 more are all exact numbers. So you keep 3 sig figs, and so you keep the 1, the 3, and the 5, and that's where the dot is. So that's 135 grams of NaCl produced from 53.2 grams of Na. You do the same thing with chlorine. So you take the mass of chlorine that is given, 65.8 grams of chlorine, multiply by the first conversion factor that uses the molar mass of chlorine. So with the grams on the bottom and 1 mole of chlorine on top. This way the grams of chlorine cancel. The second conversion factor comes from the chemical equation coefficients, and it says that we make 2 moles of sodium chloride per mole of chlorine. This way the moles of chlorine cancel. And then we multiply by the molar mass of NaCl because we want to go back to grams, and the moles of NaCl cancels. So in the calculator, you do 65.8 times 2 moles of NaCl times 58.44 grams of NaCl and divide by 70.90 grams of chlorine. And it's 108.4725, etc. grams of NaCl. Again, we need to keep 3 sig figs. The molar masses have 4 sig figs. All the other number of moles are exact. So we keep 108. What comes after the 8 is a 4. So we keep the 8 and 8. And so it's 108 grams of NaCl produced from 65.8 grams of chlorine. And we can see with the amount above that the least amount of product made is from the chlorine. It's 108 grams versus 135 grams. So you can make less product from the 65 grams of chlorine than from the 53.2 grams of sodium. So chlorine is the limiting reactant. It limits the amount of product that you can make to 108 grams of sodium chloride. So that means the theoretical yield is 108 grams of NaCl. That's the maximum amount you can do. And so that's called the theoretical yield. So there is this question added to that example, and it's if the reaction produced 86.4 grams of NaCl, what is the percent yield? So that 86.4 grams of NaCl actually produced, is what we call the actual yield. It's what we actually produced versus the 108 grams that we theoretically should make. Then we can calculate the percent yield. The percent yield is the actual yield over the theoretical yield times 100. So we take 86.4 grams of NaCl over 108 grams of NaCl times 100, and that's 80%. So notice how 80% here has 3 sig figs. So it's 80.0 to show 3 sig figs because our two masses from the actual yield and theoretical yield had 3 sig figs. So that means this 80% here means that you are actually making only 80% of what you could make if the reaction was really complete. Let's look at another example here where we have two products made from two reactants. And so if 11.5 grams of carbon reacts with 114.5 grams of copper, let's see, copper 1 oxide, because copper here is Cu plus. So from copper 1 oxide, what is the limiting reactant and theoretical yield? So same question as earlier. We are given the chemical equation here, and it's balanced. So it's a Cu2O solid plus carbon solid will make 2 copper solid and CO, the carbon monoxide gas. So when you have this question asking about which one is the limiting reactant, the procedure is always to calculate how much product you can produce from each reactant, because you're given masses for each reactant. So you calculate separately how much you can produce from the 11.5 grams of carbon and how much you can produce from 114.5 grams of Cu2O. And here you can choose either or product, right? And we have chosen copper. So from the 11.5 grams of carbon, you need to calculate how much copper you will make. And so again, the way to change the moles of copper, the moles of carbon to moles of copper is by using the coefficients of the balanced chemical equation. And because here you're given grams, so you will need to change those grams into moles, because you cannot change grams of carbon directly to grams of copper. It's not possible. You need to go through moles. And the moles, then you can change them using the moles proportion given by the coefficient of the chemical equation. So the first step is to convert grams of carbon to moles of carbon using the molar mass of carbon. Then from the moles of carbon, using the coefficient of the equation that says 1 mole of carbon makes 2 moles of copper, you will change the moles of carbon to moles of copper. And then after that, you can change the moles of copper produced into grams of copper using the molar mass of copper. Same thing you will need to do with the mass of the other reactant. So the 114.5 grams of Cu2O, you will use that as your given amount and change that into moles of Cu2O using the molar mass of Cu2O. This then will allow you to change the moles of copper 1 oxide into moles of copper using the coefficients from the balanced equation. So here it says that 1 mole of Cu2O will produce 2 moles of copper. And then from the moles of copper, you can go back to grams of copper using the molar mass of copper. And so once you have those two products amount, you compare them, and the smallest amount determines the limiting reactant. So let's do those calculations and start with carbon. So the given amount of carbon is 11.5 grams of carbon. That's in the numerator. You multiply by the first conversion factor that changes the gram of carbon into moles of carbon using the molar mass of carbon. And the molar mass is written such that the grams of carbon are on the bottom of the conversion factor and the moles on top. This way we can cancel units of grams of carbon. Multiply by the second conversion factor changes the moles of carbon to moles of copper. And here it's 1 mole of carbon makes 2 moles of copper. We have the moles of carbon on the bottom, so we can cancel moles of carbon. The next step, we'll need to cancel the moles of copper. And so the next step is to change the moles of copper into grams of copper using the molar mass of copper. And so we have the grams on top and the moles on the bottom so that we can cancel units of moles of copper. In the calculator, you do 11.5 times 2 moles of copper times 63.55 grams of copper divided by 12.01 grams of carbon, and that's it. Equals, the calculator answer is 121.70274, etc. We need to keep 3 sig figs because the given amount has 3 sig figs and both molar masses have 4 sig figs. All the other number of moles are exact. So you keep 120 and the 1 will become a 2 because what comes after the 1 is a 7.7. So you need to round it up to a 2. So it's 122 grams of copper made from 11.5 grams of carbon. You do the next calculation with the amount of the other reactant, and that's 114.5 grams of copper 1 oxide. So multiplied by the first conversion factor, that is the molar mass of copper 2 oxide, sorry, copper 1 oxide. And so the molar mass is written as a ratio with the moles on top and the grams on the bottom, because we can cancel then the units of grams of copper 2, copper 1 oxide. Multiply by the second conversion factor, that is going to change the moles of Cu2O into moles of Cu. And we have 1 mole of Cu2O producing 2 moles of copper. So this way moles of Cu2O cancel. And the next step should cancel the moles of Cu. So it's the molar mass of copper with the grams on top and the mole on the bottom. This way we cancel units of moles of Cu. So in the calculator, you do 114.5 times 2 times 63.55 divided by 143.10 equals. The calculator answer is 101.6977. Here, the given amount has 4 sig figs. The molar mass of copper has 4 sig figs. The molar mass of Cu2O has 5 sig figs. So the limiting amount of sig figs comes from the molar mass of copper and the given amount of Cu2O. So it's 4 sig figs. So you keep 101.69. So what comes after the 6 is a 9. So you run the 9 into a 7. So it's 101.7 grams of copper made from 114.5 grams of Cu2O. So if you compare the two amounts of product made, you can see that the least amount of product is 101.7 grams of copper from the copper 1 oxide. So then the Cu2O is the limiting reactant. It's not the carbon, even though there's a much smaller mass of carbon. So the limiting reactant is the copper 1 oxide, and the theoretical yield is 101.7 grams of copper. That's the amount of product that theoretically you should be able to make. However, as you can see in this slide, if the reaction produced 87.4 grams of copper, what is the percent yield? So this amount of 87.4 grams of copper that is produced is the actual yield. It's what you actually were able to gather from the product of this reaction. So it's the actual yield. It's not the theoretical yield. Theoretical yield is the number we got earlier, the 101.7 grams of copper. And so to calculate the percent yield, you do the actual yield over the theoretical yield times 100. And so that's 87.4 grams over 101.7 grams of copper times 100. And that comes down to 85.9% yield. So the percent yield means what you are actually producing is only 85.9% of what you should be theoretically able to produce from those amounts of reactant. you know that you rarely get the theoretical yield as an actual yield. So let's go through some concept check now. And it's important that you pause the video and try solving this on your own before you watch the answer. That's the only way to learn. So the problem is, suppose 321 grams of methylamine, and methylamine is CH3NH2, and 475 grams of oxygen are mixed together. You're given the chemical equation and it's balanced. And the first question is how many grams of water should be produced? And there is 2 more questions after that. So we'll focus on the first questions here. How many grams of water should be produced from these 2 masses of reactant? The methylamine and the oxygen are the 2 reactant, and we're given masses for them. So here we need to find how many grams of water should be produced, but we don't know which one is the limiting reactant. So it is implied that you need to find which one is the limiting reactant. And so to find out which one is the limiting reactant, you will calculate from each of the reactant mass. You will calculate the amount of product, and here it's water that you want to know. So you will calculate the amount of water you can make from each of the masses of the reactant. And the one that has less water produced will be the limiting reactant. And that's the amount that you should be able to produce. So let's start with methylamine. So let's write the concept map. So we'll start with the grams of methylamine. And as we know, we cannot change the grams of methylamine into grams of water directly. The relationship between methylamine and the water is in moles, and it's given by the coefficient of the balanced chemical equation. So that means we need to change the grams of methylamine into moles of methylamine using the molar mass of methylamine. Then using the coefficient from the balanced chemical equation, we change the moles of methylamine into moles of water. And then we can change the moles of water into grams of water. So that's how we will get the grams of water produced from the grams of methylamine, assuming that we have enough of the oxygen, of course. So we need the molar mass of methylamine for the first step. Then we need the mole ratio from the chemical equation coefficients for the second step. And then we need the molar mass of water. So we need to gather all this information before we can start. So let's calculate the molar mass of methylamine first. Methylamine is made of 1 carbon, so you take the molar mass of carbon from the periodic table, and that's those numbers that have decimals that are below the name. So carbon, it's 12.01, and it's 1 carbon, so just 1 time. Hydrogen, the molar mass of hydrogen is 1.01. And be careful here, there is 2 places where you have hydrogen. First, you have 3 hydrogens bonded to carbon, and then 2 hydrogens bonded to nitrogen. So it's 5 hydrogens in total. So you need to do 5 times 1.01 for the mass of hydrogens. And then there is 1 nitrogen, so plus 14.01 for the nitrogen. You add all this up, and it's 31.07 grams per mole. Now the molar mass of water. So water is made of 2 hydrogens, so you take 2 times the molar mass of hydrogen, so 2 times 1.01, plus 1 time the molar mass of oxygen, and that's 16.00. And that's a total of 18.02 grams per mole of water. The last information we need is the mole ratio that you obtain from the chemical equation. So the chemical equation here shows us that from 4 moles of methylamine, we can make 10 moles of water. So 4 moles of methylamine will produce 10 moles of water. So that's the mole ratio we will need in this case. You only use the coefficients that are useful here and that are connected to the reactant and the product that are in the question. So now we are ready to do the full calculation. And the calculation will start with the given amount of methylamine. So 321 grams of methylamine. That's the given amount. You multiply that by the first conversion factor. The first conversion factor comes from the molar mass of methylamine, and it's written such that the grams of methylamine are on the bottom and the 1 mole of methylamine is on top. This way we can cancel the grams of methylamine. Next, you want to change the moles of methylamine into moles of water, and so you use the mole ratio. The mole ratio should be written such that the 10 moles of water are on top and the 4 moles of methylamine on the bottom, so that we can cancel the units of moles of methylamine. Next, you need to cancel the moles of water in the final conversion factor. And the final conversion factor comes from the molar mass of water. And so you're using the 18.02 grams of water on the numerator and per mole in the denominator. This way we cancel moles of water as units. So then you are ready to do the calculation in your calculator. So it's 321 times 10 moles of water times 18.02 grams of water divided by 31.07 and divided again by 4 moles of methylamine. The calculator answer is 465.43, 45, etc. Here, because the given amount has 3 sig figs, the 2 molar masses have 4 sig figs, and all those mole numbers are exact numbers. So then the limiting amount of sig figs is 3 from the given amount. So we keep the 4, the 6, the 5. What comes after the 5 is the 4, so you keep the 5 a 5. So it's 465 grams of water produced from 321 grams of methylamine. So that's only half of the work done here, right? To find which one is the limiting reactant, we don't know yet if we make more or less with the 475 grams of oxygen. So we still have to do that calculation. And then we'll compare that to the 465 grams of water produced from the methylamine. So we start over, and now we do the calculation with the grams of oxygen. So let's write the concept map first. So from the 475 grams of oxygen, we will need to change them into moles of oxygen, because we need the moles of oxygen to change them into moles of water using the coefficients from the balanced chemical equation. And then once we have the moles of water, we can change them back to grams of water using the molar mass of water. So we will need the molar mass of oxygen, and so oxygen here is the diatomic molecule O2. We will need the mole ratio between oxygen and water. That's given by the chemical equation coefficients. And then we will need the molar mass of water. So let's gather all this information first. So molar mass of oxygen. Oxygen is made of 2 atoms of oxygen. So you do 2 times 16 grams of oxygen per mole of oxygen. And that's 32.00 grams of oxygen per mole of oxygen. Molar mass of water, we know already it's 18.02 grams per mole. And then the mole ratio. The mole ratio comes from the chemical equation coefficients. And here we can see that we are producing 10 moles of water from 9 moles of O2. So it's 9 moles of O2 equals 10 moles of water. So we are ready to write the full calculation, starting with the given amount of 475 grams of oxygen. So be careful here, oxygen is the oxygen gas that is used as a reactant here. So 475 grams of oxygen, you start your calculation with that in the numerator. Then you multiply by the first conversion factor that has, so it's the molar mass of oxygen, and it has the grams on the bottom and the mole on top, so that we can cancel grams of oxygen as a unit. The next step needs to change the moles of oxygen into moles of water. And so it's the mole ratio that we will use now. And we will write the 9 moles of oxygen on the denominator so that we can cancel moles of oxygen units. And so the 10 moles of water are on top. And multiply by the third conversion factor that is from the molar mass of water. And we write it such that we have the grams of water on top over 1 mole of water, because this way we can cancel the units of moles of water. In the calculator, you do 475 times 10 moles of water times 18.02 grams of water divided by 32.00 grams of oxygen and divided again by 9 moles of oxygen. And the calculator answer is 297.20486, etc. Here we need to keep 3 sig figs again, because the given amount has 3 sig figs. Both molar masses have 4 sig figs. All the mole numbers are exact numbers. So the limiting amount of sig figs comes from the given amount, and it's 3 sig figs. So we keep the 297. What comes after the 7 is a 2, so you keep the 7 a 7. So 297 grams of water are produced from 475 grams of oxygen. Remember that we still don't know which one is the limiting reactant between methylamine and oxygen. So we need to compare this amount of grams of water to the mass of water that can be produced from methylamine. And so it's 465 grams of water that can be produced from the 321 grams of methylamine. And because we can make less with the amount of oxygen, that means oxygen is the limiting reactant. It limits the amount of water that can be produced to 297 grams. So this amount of 297 grams is the theoretical yield. It's what you should be able to produce. That's the minimum amount that you can get, or the maximum amount. So that answers question A. Question B, what is the theoretical yield of nitrogen gas? So now we know which one is the limiting reactant, right? We know it's oxygen. So here, to calculate the theoretical yield of nitrogen gas, we will use oxygen, because oxygen limits the amount of product you can make. So we only need to find the mass of nitrogen gas we can produce now from this amount of oxygen. So the concept map will look like this. So we use the limiting reactant, oxygen. So the 475 grams of oxygen. We will change that to moles of oxygen using the molar mass of oxygen. Then using the balanced chemical equation coefficients, we can change that to moles of nitrogen gas. And then using the molar mass of nitrogen, we can get back to grams of nitrogen. So the quantities we will need are the molar mass of oxygen to change the grams to moles of oxygen. Then the mole ratio between oxygen and nitrogen, and that's given by the chemical equation coefficient. And then once we have the moles of nitrogen, we can go back to grams of nitrogen using the molar mass of nitrogen, the nitrogen gas, N2 molecule. So let's gather all the information. The molar mass of oxygen we calculated earlier, it's 2 times the molar mass of oxygen, so 2 times 16. It's 32.00 grams per mole of oxygen. The molar mass of N2, it's 2 times the molar mass of nitrogen, and nitrogen is 14.01 grams per mole. So that's 28.02 grams per mole of nitrogen gas. And we need the mole ratio between oxygen and nitrogen in this reaction. And here we can see from the chemical equation that we have 9 moles of oxygen that can produce 2 moles of nitrogen. So 9 moles of O2 equals 2 moles of N2. So now we are ready to do the full calculation. And we will start with the given amount of grams of oxygen. So the 475 grams of oxygen, multiplied by the first conversion factor, that is the molar mass of oxygen, written such that the grams are on the bottom and the mole is on top, because this way we can cancel the grams of oxygen. The next conversion factor should change the moles of oxygen to moles of nitrogen. And we will have the moles of oxygen on the bottom and the moles of nitrogen on top, because this way we can cancel moles of oxygen units. And the third conversion factor will change the moles of oxygen into grams of oxygen using the molar mass of oxygen, of nitrogen. So change the moles of nitrogen to grams of nitrogen using the molar mass of nitrogen. And so we have the grams on top of the conversion factor and the moles on the bottom. This way we can cancel moles of nitrogen units. So then we are ready to do this in the calculator, and it's 475 times 2 moles of nitrogen times 28.02 grams of nitrogen divided by 32.00 grams of oxygen, and divided again by 9 moles of oxygen. The calculator answer is 92.427, etc. The given amount has 3 sig figs. The 2 molar masses have 4 sig figs, and all the number of moles are exact. So the least number of sig figs is 3 from the given amount. So we keep the 92.4. What comes after the 4 is a 2, so you keep the 4 a 4. And that's 92.4 grams of nitrogen made from 475 grams of oxygen. And that's the theoretical yield of nitrogen. That's the maximum amount we can make from this amount of oxygen. So that answers question B. Finally, question C here. What is the percent yield of water if 189 grams is actually produced? So the formula is the actual yield over the theoretical yield times 100. So here the actual yield is 189 grams that is actually produced. That's what you actually get from this reaction. The theoretical yield is the theoretical yield of water. So it was the 297 grams of water that you could produce from the grams of oxygen. So you put that on top of each other and then times 100, and the calculator answer is 63.63, 63, etc. Because both masses are given with 3 sig figs, so we need to keep 3 sig figs. Remember how the 100 is an exact number and it's not limiting. So we will round this to 63.6. What comes after the 6 is a 3, so we keep it a 6. And that's the percent yield here. That's a poor percent yield, actually. You're only making 63.6% of what you could make here of the water that could be produced.